Well, what we want to do today is, first of all, come up with the derivative formulas for all 6 trig functions. Now that's a pretty aggressive plan, but that's one of the things we're going to do. So right off the bat, I would like to take the derivative of the sine of x. Now, the only way you can take a derivative right now, if you don't have a formula, is to derive it, and that's using the definition of the derivative, which we now know from last day is the limit as delta x approaches 0 of, well, if this is my f of x, then I want f of x plus delta x minus my f of x all over delta x. So whatever the answer is, it's going to come from this statement here. This is the derivative of the sine function. Now, if I can manipulate this, I will, but right now I have 2 different arguments going on. I have one argument that's x plus delta x and one argument that's x, and it's going to be kind of hard to work with them. So off to the side, let me remind you, we have an identity. Sometimes we call them the alpha beta identities, where if I have the sign of a sum or difference, I know it's this, sine alpha cos beta plus or minus sine beta cos alpha. That's a really, really important identity right there. And if I do this expansion right here, then I may get something that's useful. So let's do exactly that. So this is going to be the limit as delta x approaches 0 of. Now let's expand the sign first. So it's going to be sine cos, sine cos. So it's going to be sine x cosine delta x plus sine delta x cos x minus the sine function all over delta x. Now I haven't done any calculus yet. Writing this down, I'm just doing the definition of the derivative. That is the answer. I just don't know how to evaluate it yet. But by doing this expansion, we've set ourselves up to do a little bit of factoring. So you notice I have a sine x term here, and I have a sine x term here. I can put those 2 together. Now remember, the limit of a sum is the sum of the limits, so I can pull apart limits. And remember, in general, if I said I have a plus b over c, I know that's this. I know I can always pull apart a quotient by leaving the denominator. So we're going to do a little bit of algebra and pull this apart, but I want to put the sine terms together. So I'll have sine x cosine of delta x minus sine x over delta x. Okay. Plus, now what's left? Well, let's see. I just took that term and that term, so the only thing left would be that term. Now, in case you're wondering, is what we did valid? Well, remember, I said the rule of thumb is always cover up the word limit. Okay, so let's go back to the beginning. If I cover up the word limit, is that quantity equal to this quantity? Yes, it is. Is this quantity equal to the sum of these 2 quantities? Yes, they are, because I just rearranged them. So therefore, I know the limits are equal. Now, at this point, you say, well, what can I do? Well, again, the limit of a product is the product of the limits. So in this case, I can clearly factor out the sine term. So I can write this as the limit as delta x goes to 0 of the sine function times the limit as delta x goes to 0 of what's left, which in this case would be, let's see. Actually, you know what? I have a cosine delta x minus 1. I'm going to factor out a negative. I'm going to factor out the negative of the sine. Then I can switch the order of subtraction, and that will be 1 minus the cosine of delta x over delta x, which might look a little more familiar to us. So again, if I multiply negative sine into this quantity, I would get that back again. And then over here, I'm going to factor out the cosine term. It still has to be within the limit, by the way. And then multiply that by. All right. So all I did was a little bit of algebra. We've performed no calculus yet. The limit of a sum is the sum of the limits. The limit of a product is the product of the limits. So I took this, expanded it using an identity, broke up the quotient, and then factored within. All right, so I have this limit times this limit plus this limit times this limit. Well, now what am I supposed to do? Well, we have two identities that we proved. We have the identity, the limit as theta goes to 0 of sine theta over theta, and we have the identity, the limit as theta goes to 0 of 1 minus cos theta over theta. We have these two limits that we proved. This one is 1, this one was 0. Do I have those statements in here somewhere? Well, I do believe that I do. See that? I have both of them. You see, in this statement here, what's my theta? My theta is delta x. Delta x goes to 0, cos delta x over delta x. That's my theta. That's exactly that statement right there. And then over here, theta goes to 0, sine theta over theta. So I can easily now evaluate this entire thing. This is beautiful. You're going to like this. So what have I got? So the limit as delta x goes to 0 of the negative sine of x is just the negative sine of x because there's no delta x's there. That's not changing. This is 0. Plus, the limit as delta x goes to 0 of the cosine function. There's no delta x there, so this limit is just the cosine function. It's kind of like saying the limit of a constant is a constant. There's nothing there that's changing, so that's going to stay the same. And then we know that limit is 1. Negative sine x times 0 plus cos x times 1 is simply the cosine of x. Whoa. So what did we just prove? We just proved that the derivative of the sine function is the cosine function. And that is really, really cool. And it's ridiculously important and handy, and we're going to use this all the way through calculus. So let me draw a picture. This might help better for you to understand. I took the derivative of one trig function, and I got a different trig function. Now that seems a little odd, but maybe it'll make perfect sense. So if I were to draw a picture, just a simple picture of a sine wave. Okay, I know a sine wave kind of, goes like this, and the other direction. It's going to go like that forever and ever and ever. And I know that's 1 unit high, and that's -1, and so on. Well, one thing we do know, because the limit of sine theta over theta as theta goes to 0 is 1, that tells us that the sine function, or if I think of it this way, let me use an x. I know the limit as x goes to 0 of sine x over x is 1. But the slope of y equal x is already 1, which means that the slope of the sine function must also be 1 at the origin. So at the origin, the slope of the sine function is 1 because that limit is 1. In other words, sine's kind of acting like y equal x right there. But because of symmetry, then I know the slope here has got to be -1. And I know the slope at the peak is 0. I know the slope at this peak is 0. So imagine, if you will, I'm going to draw a graph of the slopes of the tangent lines. That's not that, it's actually not that difficult. You see, what's the slope of the tangent line here? It'd be 0. How about here? It'd be 0. How about here? It'd be 0. How about here? It'd be 0. Okay, got that covered. What's the slope of the tangent line at the origin? We just said the slope right there has to be 1, because otherwise that limit wouldn't be true. But then what would be the slope here? Well, then that would be -1. Okay, so what's the slope here? That would be -1. And what's the slope over here? That'd be +1. Okay. And this is kind of a loose graph, but if I said I want to plot the slopes of the sine, well, clearly the slope here is 1, and then here it's 0. And then here it's coming back, and over here. So the orange represents the slopes. Again, the slope here would be 1, the slope here would be 0, the slope here would be -1. And do you notice anything about the orange graph? It kind of looks like the cosine function. In other words, I know this is true. I'm showing you by just looking at the slopes. If we had just looked at the slopes of the sine function, we would have traced out a cosine function eventually. So that's kind of nice. So the sine and the cosine really are related. So if the derivative of the sine is the cosine, what do you suppose the derivative of the cosine function would be? Well, it kind of makes sense that it probably should involve the sine function in some way. So let's try that one. Let's do this derivative. Now, just like the sine function, I'm going to need to start with the definition of the derivative. In other words, it would have been absolutely impossible to come to the conclusion that the derivative of the sine is the cosine without having used this formula here. So this should be cosine of x plus delta x minus the cosine of x all over delta x. Now, cosine has an expansion, in case you forgot it. The cosine of alpha plus or minus beta. And again, this is in the opening video and opening notes that I put out, but this is one that, it's a little obscure. This one's cos, sine, sine, if you remember. So this one's cos alpha, cos beta, minus or plus, sine alpha, sine beta. Okay, that's a trig identity that if I apply it to this guy right here, then I can expand the cosine function. And my expansion would look like this. So I'm going to have cos, so cos x cosine of delta x minus sine x sine delta x minus the cos function all over delta x. Now, I haven't done any calculus yet. I just did an expansion of a simple trig formula. But now if we attack this like we did the last one, notice that I have a cos x here and a cos x here. I'll go ahead and break these up again so the cosines together and then factor it. So the algebra, if I just walked out of the room and I said, finish this problem for me, you should all be doing steps that mimic the last problem by pulling things apart and then seeing if we have those important identities right in the middle of the answer here. So let's break it apart into two pieces. The first piece being this and this. And then the second piece being this. Okay, again, I haven't done any calculus yet. If I cover up the word limit, is this quotient equal to this? Yes, by a trig identity. Is this equal to this? Yes, because that plus that gets me back to here. Okay, so I know what I'm doing so far is working. Now, the only thing left to do is I'm going to factor the cosine out, and here I'm going to factor out the sine. But if I factor out the cosine, it'll be cos minus 1. I really want it to be 1 minus cos, because that's what the identity looks like. So here we will factor out a negative cosine. We're being a little bit clever now. And what that will leave me with, if I factor out a negative cosine, then that will leave me with 1 minus the cosine of delta x over delta x. And quick check, multiply negative cosine back in. Okay, it still works. Over here, minus the limit as delta x goes to 0 of the sine function times the limit as delta x goes to 0 of the sine of delta x over delta x. Okay. Just like the last problem, at this point we can evaluate because I've got this, I call it a standalone limit. I know this limit. When we did the trig limits as practice recently, it was the same thing. You had to manipulate your statement so you got something like this all by itself, or you got something like this all by itself, because then I can say, evaluate, evaluate. But until those are standalones, I can't evaluate them. So on the left side, this is clearly the negative of the cosine. That's what the first limit would be, times 0. Minus, as delta x goes to 0, the sine function just stays the sine function because there's no delta x in the argument. And then that term is 1. So it looks like my answer is simply the negative of the sine function. So the derivative of the cosine is the negative of the sine function. It's not the sine. Now that's something that could give us trouble if we're not paying attention. So the derivative of sine and cosine are basically the other function, but this one, there was a plus or minus change. So let's do what we did before. Let's consider what the sketch would look like. Now you never have to do this, but it just kind of verifies what you said. So let's consider that what a cosine graph looks like. Now I know the cosine looks like this. So like before, well, the shape of the cosine graph, by the way, we know is exactly the same as the shape of the sine. It's just shifted. The sine and cosine graphs are identical. They're just shifted. It's called a phase shift. So if I shifted this over pi over 2, it would be the sine graph. So at this point here, I'd have a slope of 0. At this point, I'd have a slope of 0, 0, 0, and so on. Okay. Here, I know the slope of the tangent would be -1. Here, I know the slope of the tangent would be +1. Here, I know the slope of the tangent would be +1. Here, I know the slope would be -1. So let's kind of carve this out. That doesn't look like a sine wave. It looks like a sine wave that is upside down. Hence the negative of the sine wave. Good, beautiful. Now it turns out these are the only trig functions that we actually need to use the definition of the derivative for. It's kind of nice. You say, what do you mean it's kind of nice? Well, we can now use prior results. You see, one of the most important functions that we work with is the tangent function. Now let me put up here because we also have this. The derivative of this sine is the cosine. All right, here's what I'd like to do. I would like to do the derivative of the tan of x. Now, don't write this down, but I know for a fact that this would be the following limit. I know this. I have absolutely no doubt. And there is actually an expansion for that. The problem is I'd get really nasty looking limits and I can write it out, but I can't do anything with it. I wouldn't know where to go from there. This is a correct mathematical statement, but I don't need it anymore. And the reason I don't need it is because we have a very, very simple identity with tangent. We know that the tangent function is equal to the sine over the cosine. We know that the cotangent function is equal to the cosine over the sine. We know that the secant function is equal to 1 over the cosine. And we know that the cosecant function is 1 over the sine. So what we're going to do is figure out ways of differentiating quotients. That's going to be like the next big thing we do. So I started with the trig, and then we're going to go back and look at the quotients in a little bit. You're going to like this. So at the end of the day today, there's going to be basically 8 formulas. 6 formulas for trig, 1 formula for products of functions, 1 formula for quotients of functions that we will now be able to apply across the board. So I started with the trig for a reason, because I want to be able to use it for the next thing we're going to do. But the next thing we're going to do, we're going to use trig identities rather than limits to come up with the derivatives. So we're going to bank these 2 guys here, and then we're going to come back to these guys. So I'm going to take a hiatus from trig for a little bit. We will come back. There is actually a method to the madness here. So now I have a simple question. We know that the limit of a sum is the sum of the limits. The limit of a constant times a function is a constant times the limit. And we know both of those apply to derivatives. The derivative of a sum is the sum of the derivatives. The derivative of a constant times a function is a constant times the derivative. We proved that using limits. We have no doubt. So now the question is, what about the derivative of a product? I know the limit of a product is the product of the limits. I know the limit of a quotient is the quotient of the limits. And I know the limit of a composition is the composition of the limits. Do those hold for derivatives? Is the derivative of a product the product of derivatives? Well, let's actually do a really simple example. Let's suppose that f of x, let's keep it really simple, is x squared, and g of x is x cubed. Let's keep it really simple. Here's what I'd like to do. I'd like to do the derivative of f of x times g of x. Well, there's two ways I can look at this. The easy way is I can just multiply them out. So wouldn't that just be the derivative of x squared times x cubed is x to the fifth? And based on last lecture, I know that's the answer, period. That's easy. So secondly, what if I said the derivative of f of x, that which is f prime of x? Well, won't that be 2x? And if I ask for the derivative of g of x, won't that be 3x squared? So now, if we do, what's the derivative of f of x times the derivative of g of x? Well, that would be 2x times 3x squared, which is equal to 6x cubed. Great. I just did the product of the derivatives. Here is the derivative of the product. What do you think? Are these the same? No, they're not. We differentiated the product and we got 5x to the fourth. Here we took the product of derivatives and we got 6x cubed, which is not equal to 5x to the fourth. So the question I asked is the derivative of the product equal to the product of the derivatives? It is either always true or it is not. And one thing nice about mathematics, to prove a true statement is true can be very difficult. You have to maybe go through a long, arduous process. But to prove a statement is false, you only got to come up with one example of it being false. I just took two simple functions. I took the product of their derivatives, and it clearly did not equal the derivative of the product. So I can now say with certainty that the derivative of the product of two functions is not equal to the product of their derivatives, which, by the way, would have seemed like the obvious choice because we know how limits work. But it turns out the only two limit properties that extend to derivatives are the limit of the sum and the limit of the scalar multiple. That's it. None of the other properties extend. So the derivative of a quotient is not going to be the quotient of derivatives. The derivative of a composition will not be the composition of the derivatives. No, those are way more complicated. In fact, the composition part, that's next day's lecture entirely. So we need to come up with a formula for the derivative of the product because this is going to be one of the most common formulas we use all throughout calculus. Now, before I start, I'm going to show you a simple little algebra thing that I like to do because, well, I'm lazier than most people. So I like to do things because I'm lazy and I like to not waste time. Long and synthetic division are very, very powerful tools for doing things. And it's never wrong to use them in the proper context, but sometimes it can be overkill. I'm going to give you a really, really simple example. Let's suppose I have a quotient such as x over x minus 3. Okay, there's a simple rule in mathematics that says whenever you have a rational function is a quotient of polynomials. That's a rational function. You can't do anything with it unless the degree of the numerator is smaller than the degree of the denominator. This is absolute across the board. So if my numerator is a higher degree, we just do longer synthetic division. If my numerator is a lower degree, we don't do anything at all. Right now, they're the same degree, which means I technically have to do the longer synthetic division. So I'm going to walk you through both. So if I said, let's start with the long division, okay, then I'd have x minus 3 goes into x. And we know this is okay. And then we'd say, all right, we take the first term, everything has to be in descending order. So x goes into x one time. 1 times x minus 3 is x minus 3. And if you remember, you then subtract. Oh, so I need a placeholder here. I just put a plus 0 there. That's the easy way. So when I subtract, I'm going to have a positive 3. Since 3 is a lower degree than x, this must be my remainder. So that means my answer is 1 plus 3 over x minus 3. Now, if I put these together over a common denominator, I can easily see that that's my answer. Now, most of us would say, you know, long division is fine, but synthetic would have been easier. But a lot of you are rusty on synthetic. Synthetic is I look at the root of the denominator, The root is whatever x value makes this equal to 0. So the root would be 3. I put the 3 down, and then I put all the coefficients of the numerator in descending order down to the constant term. Well, the coefficient is 1, but I don't have a constant term, so I put the 0 there. So in case you forgot, synthetic division, I bring this number down, I multiply, I add, and now I'm done. That is the remainder term. Again, I've reviewed this in the previous notes and things. That's the remainder, so that must be the constant. And again, I'd get that answer. So both processes, which hopefully you're very familiar with both. You really want to be able to do both. Synthetic division, when you can use it, is always faster than long division. But remember, you can only use synthetic division if your denominator is linear. If I had an x squared or higher in the denominator, then I couldn't use synthetic. Now, there's a third way. And many, many, many years ago, I had students start coining, there was long division, synthetic division, and Brown division. Just so you know, I rarely do either one of these. They take too long. They take too long. So this is just way too much work for me. And you see, here's what I do. Because you can always add and subtract the same value to a quantity, regardless of what my quantity is. If I decided to add and subtract 10, or add and subtract x, or add and subtract, root pi. If you add and subtract the same quantity to something, it doesn't change the value. So what if I said, I'm going to put -3 plus 3? Have I changed the value at all? No, I just added 0. But then if I pull apart this quotient, I have x minus 3 over x minus 3 plus 3 over x minus 3, which is simply 1 plus 3 over x minus 3. This is what I do most of the time when I'm doing things. I don't even bother with long or synthetic division. I just add and subtract the appropriate term in the numerator. How do I know what's the appropriate term? Well, if I got an x minus 3 in the numerator, then it would equal 1. So I did -3, not some other value. You never have to do this, but it can be ridiculously fast if I do. So let me do something that's slightly more complicated, okay? What if I had something like this? I've got x squared minus 4 over, let's say, x plus 1. Well, clearly long or synthetic division would be perfect. But I know that x plus 1 times x minus 1, I know that equals x squared minus 1. So if my numerator looked like x squared minus 1, then this would factor in really easy. So I'm going to do this, plus 3 minus 3. Now my numerator is x squared minus 1 over x plus 1. Because I put those two together, minus 3 over x plus 1. And this is then when I do the long division, or I'm sorry, when I factor and cancel. Now I might have blown some of you away. This is equal to this. Whether you do long or synthetic division, this is equal to this because this is equal to this, which is equal to this. These are the sort of algebraic tricks you can always perform when you have functions as a time saver, but I'm not going to do these as a time saver today. I'm going to do these as a way of manipulating our limit quotient, which we're about to do, because we're now going to do some really complicated stuff that we actually need to do a step like this to make it work. So here's what we're going to do. We're going to derive the derivative of f of x times g of x. We're going to derive this, and we're going to derive it using the limit because there's no other way to get the answer. So this is going to be the limit as delta x approaches 0 of f of, oops, let me use parentheses here, f of x plus delta x, g of x plus delta x. That would be this term as x plus delta x minus f of x times g of x all over delta x. Now, absolutely guaranteed, that is the derivative because we just used the definition of the derivative. The problem is, I basically got a dead end here. I have nowhere to go right now. I can't do anything with that. But if I add the appropriate terms to the numerator, add and subtract, I should say, the appropriate term to the numerator, I might be able to do like I did with the sine and cosine. In other words, pull it apart and individually evaluate. And that's really the key. So what I'm going to do is I'm going to add and subtract. I'm going to write it down. I'm going to add and subtract f of x plus delta x g of x. That's the term that I'm going to add and subtract to my numerator. Now, where did that come from? I'm guessing whoever figured this out probably did a little bit of trial and error, but we don't need to. We know exactly what to add and subtract. I'm going to add and subtract exactly that quantity. So let me rewrite this then. This is actually quite beautiful mathematics if you follow through, because nothing that I've done is even a little bit complicated yet. I'm just writing down a definition. I need a little bit of room now. So minus f of x plus delta x g of x plus f of x plus delta x g of x. It's gonna be hard to fit that last piece in. And then the last piece back there, right there, minus f of x g of x. Didn't plan that very well. And then all of this is over delta x. I absolutely know that this quantity is equal to this quantity because I added and subtracted the exact same amount to the numerator. But what that will allow us to do now is pull this apart as the sum of two separate limits. Because again, the limit of a sum is the sum of the limits. So we're going to pull it apart. And I'm going to have two different limits here. I'm going to have the limit as delta x goes to 0 of this piece plus this piece. Let me see if I can fit that whole thing in here. Okay, barely. Okay, that was pretty awful looking. All right. That's, I can't even read that. That's fg minus f of x, g of x. There we go. All right. Again, if I cover up the word limit, I know that this quotient is equal to this quotient because I added and subtracted the same quantity. But then I said, now let's separate it. So if I took this quotient and I added it back to this quotient, I would get this quotient again. So there is no doubt. Now I have only one step left, and that is to factor. Do you see anything that's a common factor? Well, here, clearly I have the f term. The limit of a product is the product of the limits. So I have f of x plus delta x times the limit as delta x goes to 0. Well, what's left? G of x plus delta x minus g of x all over delta x. Okay, that's the first piece. Now in the second one, it looks like I can factor out perhaps the g of x term. And then that would be multiplied by what's left would be the f of x plus delta x minus f of x term. Okay, and now we're done. We're done. This looks really big and huge and scary. Well, that and that we should recognize. That's the definition of the derivative for g of x. The limit is delta x goes to 0 of g of x plus delta x minus g of x over delta x. That is g prime of x. That is f prime of x. That's the definition of it. So what are we left with? Well, as delta x goes to 0, f of x plus delta x just approaches f of x. So the limit is f of x. By definition, that is g prime of x. As delta x goes to 0, g of x just stays g of x, nothing's changing. And finally, that is just, and this is our answer. This is the derivative of a product of functions. Now, this is very powerful, very useful, and it's actually really, really easy to remember, believe it or not. So I'll write it down. The derivative of f times g is f of x times g prime of x plus g of x times f prime of x. Now, remember, in mathematics, we basically have things like the formula that does this is called the formula that does this formula. We generally name things after what they do. probably the single most important formula, maybe in all of mathematics before calculus, and probably the most used formula in calculus, is that formula that when you have a slope, when you have a point and you have a slope and you want the equation of the line, you use the point slope formula. Probably the most used formula in all of mathematics history. And it's not very creative, right? The point slope formula, because I have a point and I have a slope. Well, in math, formulas that do this are usually called the formulas that do this formula. So I have a product of functions. What is the rule for taking the derivative of the product of functions? We have a really clever name for this. It's called the product rule. Yeah, that was the best we could do, you know. You'd think we'd come up with something really cool and clever, you know. I don't know, some really, the Zephyr formula. I don't know, there's something, no, it's called the product rule. Again, not very interesting, not very exciting, but it's how we take derivatives of products. So let's do a couple of examples of product rule, just so we understand what's going on. Now, if I had a product of polynomials, it's far better to multiply them out first, then take their derivative, than to use the product rule on them, because if I can multiply things out first, it's always faster to do that. Product rule is not designed for products of polynomials. Product rule is designed for things that I cannot multiply out. So for example, y equals x cubed sine x. I want the derivative of this. Right now, it's a product of functions that I cannot write in a cleaner, simpler manner. So dy dx, which is the derivative, is, I'll write it out formally, first times the derivative of the second plus the second times the derivative of the first. This is exactly what we do when we do product rule. Now, I haven't actually taken any derivatives yet, but I've laid out the groundwork. So now, the derivative of the sine function we just determined is the cosine function plus the sine function. And then yesterday or last day, we know how to do this derivative. That's 3x squared. Now my calculus is done. That is an answer. Now, is this the best answer? Well, it turns out, and you're going to get conditioned to this because I'm going to remind you every day forever. Whenever you take a derivative, there's the first application you're going to learn, not yet, I mean, that's coming up. The first application of a derivative is always, where does the derivative equal 0? And then later, where's the derivative positive? Where's the derivative negative? But the most important thing about a derivative is always, where does it equal 0? And the easiest way to determine where a derivative equals 0 is to have your derivative in a factored form. So as a general rule, it doesn't even matter the situation. You always factor a derivative if you can, if it's easy. So I'm looking at this going, yeah, I clearly have common factors. I think x squared is my common factor. So I'm going to factor out an x squared, and that would leave me with x cosine. Now, generally, I don't want to put the 3 after the sine, so I'll say plus 3 times the sine. And this answer here is generally considered the best because it's the most useful. And you're going to hear me say this about a bazillion times. At this point, it's not about right and wrong. It's about what's the most useful answer. Because generally speaking, in a calculus context, when you take a derivative, that's not the end of the problem. That's probably the start of the problem, because I'm now going to take my derivative and answer further questions with it. You never just take a derivative and then walk away. Now, you take a derivative and you use that to answer questions. So we would want it in its most useful form. So that's probably the best answer I can give. All right, let's do another one. We don't have that many different functions, so let's do one with the cosine now. Let's say y equals 4x to the 6th times the cosine function. You know, keep it real simple. Same concept, nothing complicated here. So when I take this derivative, the first times the derivative of the second plus the second times the derivative of the first. Now, you notice I'm putting parentheses around the quantities. That's actually necessary because d dx is an operator. it's going to operate on what follows. If I don't use parentheses, then technically I'm saying it's operating on every single thing that follows, when that's probably not what I mean. So you always use parentheses with that. So this would be 4x to the 6th times the negative of the sine function plus cosine times 24x to the 5th. Now, do I have any common factors here? Well, definitely an x to the 5th, and with the 4 and the 24, probably a 4. So how about 4x to the 5th? Now, what's left? I've got an x, I've got a negative sign, so negative x sine x. And then over here, looks like just a 6, so plus 6 cosine. Now, you could write those in reverse order. That wouldn't make any difference, but that's the factored form. That's the best answer I can give. So these are some simple examples of how the product rule is actually used. Again, the derivative of a product, pretty straightforward. Now, I'm laying it out right here, but it doesn't take you very much practice before the first thing you're going to write is actually that line right there. See, if I say out loud, first times derivative of second plus second times derivative of first. Once I get the hang of it, I don't necessarily have to write that step right there. I can go right to the answer. And that's better over the long term. All right, now that's the product rule. Product rule we love, it's easy. And in fact, it's very forgiving because it's a sum of two products. So if I somehow got things out of order, or I just simply multiplied in the reverse order, we know that it would not change the answer because multiplication and addition are both commutative. But subtraction and division are not commutative. So if I have a quotient or a difference, order does make all the difference in the world. No pun intended. So now what if I want to do the following? I want to do the derivative of f of x over g of x. Ooh, this one's a bit more complicated now. So this one is quite huge, okay? This one here, we're going to develop, I'll give you a hint, something called the quotient rule, okay? And this is going to be the limit as delta x goes to 0 of f of x plus delta x over g of x plus delta x minus f of x over g of x all over delta x. Now, this is going to require some serious manipulation, okay? And in order to get this to work for me, I first need to make this one quotient. Now, I showed you guys this the other day. You can spend all day getting a common denominator, doing all that and then manipulating, or you can just take care of this in the first step. You see, I want one quotient. Right now, I have two quotients in my numerator. So the common denominator of the quotients in my numerator is simply g of x plus delta x times g of x. So I'm going to multiply numerator and denominator by that quantity. When I do that, I will be left with just one quotient that I don't have to be clever. I don't have to do any manipulation of. So what I'm going to get next is the limit as delta x goes to 0 of. So when I multiply this into here, those will cancel. And I will have f of x plus delta x times g of x. When I multiply this into here, the g's will cancel, and I'll have minus f of x, g of x plus delta x. When I multiply, yeah, that's my numerator. Now my denominator, so I'm actually done now with my numerator. My denominator would be this times all of that. This is just simple algebra, but most people take a really long time to get there. No matter what route you took, you got to get to here at some point. So I multiply top and bottom by the common denominator, and therefore I have no more quotients within my quotient. Now, like we did with the product rule, I want to be able to pull this apart and manipulate it so that I can see an f prime and a g prime, but I can't do it yet. So I have to figure out what are the appropriate terms to add and subtract. This time, I'll write it out. I'm going to add and subtract simply just f of x times g of x. This one's a little bit easier. So I'm going to just add and subtract f of x times g of x. So I'll just go ahead and write it right here. I'll be lazy. Okay. I'm going to write it minus f of x g of x plus f of x g of x. Great. Okay, I have not changed the value. But now how do I manipulate this? I'm going to put these two together. I'm going to put these two together because I do want them to be opposite signs, because then I can get that, you know, definition of the derivative look to it. So when I do that, now when I pull it apart, now, I'm going to have the limit as delta x goes to 0 of f of x plus delta x g of x minus f of x g of x over this nasty denominator. Okay. Minus, and now I'm putting these two together, but I'm going to put it as a minus. So minus the limit as delta x goes to 0 of, so this one will be first. If I factor, no, actually, I'm sorry. I'm going to factor out the negative. Sorry. So that would be f of x, g of x plus delta x minus f of x, g of x. There we go. It's hard to get that in there. And quick check. I put this one with this one, and these two are together, but because I factored it out as a negative, okay. All right. And, or sorry, I need the whole denominator. So I got this. Now what? Well, I know I can factor my numerator cleanly, but it's the denominator that I really don't like. Now, there's some simple algebra taking place, but the problem child right now is the delta x. The problem child is not this term, because as delta x goes to 0, this is not going to 0. This actually isn't a problem at all. So let me show you something that you guys, you know, but you may have forgotten. If I said a over b over c, that's the same as a over bc. Multiply top and bottom by c. But that's also the same as a over c over b. These three quantities are actually equal. Looking at that going, that looks really confusing. Well, what I want to do is get this guy, think of it like this. I want to get this guy separate. I want to completely separate that from the rest of the problem. And to do that, I'm going to have to make this one bigger quotient. All right, I'll use the blue pen. Clearly, this is a blue pen situation here. So my numerator now is going to be this. This is where I got to be a little bit clever. All over the limit as delta x goes to 0 of g of x plus delta x, g of x. So I used that little cool trick about quotients. Now I'm making it into two quotients again. But the reason I'm doing that is now the numerators, if I factor out the appropriate term, I'm going to have the definition of the derivative smack dab in the middle of the problem. So the last line, hopefully, because I'm running out of room here. In this case here, I want to factor out the g of x term. So I'm going to have the limit as delta x goes to 0 of g of x times the limit as delta x goes to 0 of what's left, which would be f of x plus delta x minus f of x over delta x. Okay, when I factored out the g of x is by itself. And this isn't part of a quotient because if I multiply it back in, I'll have that. Minus, now over here, let's factor out the f of x. And what I'll be left with is g of x plus delta x minus g of x over delta x. And then all of this, remember, was over that last piece of the limit. And now we're basically done. The limit as delta x goes to 0 of g of x plus delta x times g of x. Yikes. Now I'm going to go back to the top of the board here because I've run out of space. So what does that leave us with? Well, let's see. As delta x goes to 0, g of x is just g of x. This guy right here, that is the definition of the derivative of f of x. So that is f prime of x minus. As delta x goes to 0 of f of x, it's just f of x. And this guy right here, that is the definition of the derivative of g of x. That's g prime of x. Now, the problem is, what about my denominator? Well, as delta x goes to 0, g of x plus delta x just approaches g of x times g of x. And that, folks, is the quotient rule. It's kind of scary looking, but that's what it is. Okay, the quotient rule is a little scarier because it's differences and it's a quotient, so I can't get things out of order. But in words, bottom times derivative of top minus top times derivative of bottom over the square of the bottom. Now, there is an easy way to remember this. Okay, I love telling stories and I love using mnemonic devices to remember things. For example, most of you are aware of this. You know, back in the 19th century, the largest known tsunami ever recorded. It went around the world and back again. It was so big. And out in the Pacific Ocean was an island, okay? It's called the Island of Krakatoa. This is true. This island no longer exists. It's at the bottom of the sea, okay? But like the Jurassic Park movies, the Island of Krakatoa had a sister island. Remember the Jurassic Park, there were 2 islands of dinosaurs. And the Island of Krakatoa had a sister island that was destroyed. It was called the Island of Sokotoa. And the Island of Sokotoa, they likened to the lost city of Atlantis. In other words, they could do mathematics that was beyond human capabilities way back then. They could do right triangle trigonometry and do calculations that are amazing. And so most people learned all of their trigonometry skills by remembering the rules of the Island of Sokotoa. Because if you remember, it was all how you spelled it, you see. I'm guessing that's how most of you learned your triangle relationships. It's called a mnemonic device. By the way, Krakatoa really was real. Well, it turns out there's a story that a lot of you learned as children, okay? A lot of you learned this as children, and you actually have been exposed to this. There's a lot of exposure to calculus throughout your lives you didn't even realize. I mean, the cat in the hat, oh my gosh, that's how you do derivatives in calculus 3. Thing 1 and thing 2 are 2 independent variables, and it's a whole story. But if you think about Snow White and the 7 engineers, or vertically challenged men, they used to be politically correct, but the 7 engineers every day would sing the quotient rule on their way to work in the mines because they were engineers. So if we rewrite the formula, let's call the numerator high and the denominator ho. Then technically, when I differentiate this using shorthand notation, it would be ho times the derivative of the numerator, okay, minus high times the derivative of the denominator over the square of the denominator. Ho d high minus high d ho over ho ho. In fact, every day they would sing this to work. Ho d high minus high d ho all over ho ho. And then they do that annoying whistling thing. See, you learned it as hi ho, which is actually incorrect. That would be, bad commutativity. And as children, most children aren't really good at doing differential calculus. So we kind of dumb down the song for kids. But it turns out, if you sing the song correctly, you will be singing the quotient rule. Ho d high minus high d ho all over ho ho. Okay, or just in formula form. I don't really care how you remember it, but that's the formula, and there really isn't a lot of grace given if you make a mistake. Now, where do we use quotient rule? Well, real simple. If you're given a quotient of things that cannot be simplified or written more conveniently as a product, then you would use the quotient rule. So let's do a very simple example of quotient rule here. I would like to take the derivative. Okay, somebody needs to be muted there. Let's say I have 3x plus 4 and 2x squared minus 1. I'll keep it real simple. Now, I cannot do anything with this quotient. Okay, I cannot simplify it. I can't factor it. I can't manipulate it. And I'm asked to take the derivative of this quotient. So the quotient rule says ho d high minus high d ho all over ho, or just ho squared, if you will. Now, I don't know what the answer is, but I've laid out the template to find the answer. Okay, I still have to take the derivatives, but notice where the derivatives sit, and notice there's a minus sign between them. So now when I write this out, 2x squared minus 1, the derivative of 3x plus 4 is simply 3. By the way, I must remind you, you have to use parentheses here. Not using parentheses, you're going to say something very different, and you're going to make silly mistakes. The derivative of 2x squared minus 1 is simply 4x. And then all of that over 2x squared minus 1. So now if I walk away, I have correctly stated the derivative. But I don't have a very useful answer because clearly my numerator, I can distribute, combine like terms, and who knows, I might even be able to factor the result. So I'm really a long way from being completely finished. I'm done with the calculus. The rest of the problem is simple algebra. So let's clean up the numerator. So that would be 6x squared minus 3. Here, that would be minus 12x squared minus 16x. Now, should I multiply the denominator out? The answer is no. Remember, I said you want derivatives in a factored form. You know, what if my denominator had a really high degree? None of you would think about multiplying that out. So the fact that it's squared, no, leave it squared. That's more useful. Okay. And finally, let's combine like terms. So I have negative 6x squared, negative 16x, negative 3, all over 2x squared minus 1 squared. Now, if I could factor the numerator, I would. It turns out it's not factorable. So therefore, this is the best answer I can possibly give. That is the derivative of that quotient, and that is using the quotient rule. So we've developed these two very, very powerful rules. They're formulas. You just have to use them, practice them over and over. Now, I have posted notes on product rule and quotient rule. I've also got posted notes, or excuse me, a posted video with examples of it that you should watch after today because you'll now understand where everything came from. So now let's go back to the trig stuff that we did earlier. Because I said we can derive all of the rest of the trig formulas by simply using quotient rule. Now that we have a quotient rule, that makes our life much, much simpler. So let's do this. Again, I want to derive the derivative of the tangent function, but rather than do it as a limit, let's do this as the derivative of sine over cosine, because that's significantly easier to do it that way. What happens is all throughout this course is every time we develop something, we can use that result perhaps to do the next thing. You don't always have to start from scratch. I really don't want to use a limit for this guy. That'd be too complicated. So the quotient rule, okay, bottom times derivative of the top minus the top times the derivative of the bottom over the square of the bottom. I'll write it like that. Okay, so that's cos, and then the derivative of the sine function is simply cos minus the sine, and then the derivative of the cosine function we know is the negative of the sine over the square of the cos. Okay, so let's clean this up a bit. On top, I now have cos squared plus sine squared. All right, so that's a great final answer, right? Wait a minute. Cos squared plus sine squared, Isn't that just one? And I said earlier, the reciprocal of all trig functions are just another trig function. The reciprocal of the cosine is the secant. So the reciprocal of the cosine squared is the secant squared. And it turns out the derivative of the tangent function is the secant squared. Okay, so whether you saw that coming or not, that's where we got it. Now, our job is to just practice it enough to where we remember it. You're never going to have to rederive it. But the nice thing is, if you forget it, you can easily rederive it because you know sines and cosines. Beautiful. All right, let's do the cotangent next, because the cotangent is going to look a lot like this. A lot of the moves are going to look the same. So the derivative of the cotangent of x. Now the cotangent in terms of sines and cosines is cosine over sine. I'm going to put it down here this time. So I have the bottom, and let's just go ahead and write it this time, times the derivative of the top. But without, I'm not going to write the derivative of the top. Let's just take the derivative of the top, and that would be negative sine x minus the top times the derivative of the bottom all over the square of the bottom. Now, you don't have to write the d dx of the next thing. You could just take the derivative. That's what we did. Technically, this is d dx cos. Technically, this is d dx sine. We just went ahead and did it. That's correct. That's what you're going to do in general. So let's clean up the numerator. So that's the negative of the square of the sine function minus the square of the cosine function all over the square of the sine function. You know, if I factor a -1 out of the top, then I get this. Oh, isn't that just 1 again? So I have -1 over the square of the sine function. The reciprocal of the sine function is the cosecant. So this answer is negative cosecant squared. The derivative of the cotan function is the negative of the cosecant squared. Now, just understand this. Cosecant and cotangent are far and away the least used of the trig functions, but they're still there. And so we still have to know how to work with them when we see them. You just see them less than everything else. We probably see sine and cosine quite a bit more. Now we still need secant and cosecant, but those are going to be a little bit trickier. We have to be a little bit more clever. So I'm going to show you a nice little trick. I like shortcuts, and whenever I can use a shortcut, I do. So I'm going to show you a really simple shortcut. I know, let's say that we know how to find the derivative of some function. I know how to find the derivative of whatever it is. This is true for any function f of x if I know how to find it. Okay, we know if f of x is a polynomial, we know how to find it. We now know 4 of the trig functions. So let's just suppose in general, I have an f of x and I know how to find its derivative. I want you to find the derivative of the reciprocal of f of x. So would the answer be the reciprocal of the derivative? No, doesn't work that way. I want to do the derivative of the reciprocal of any function. How would I do that? Quotient rule. So this is going to be the bottom times the derivative of the top minus the top times the derivative of the bottom. I'll just write it as f prime of x over the square of the bottom. Now, what makes this one really nice, derivative of a constant is 0. So I have f times 0. So what's left? Just that term and the denominator. So this becomes negative f prime of x over the square of f of x. Now, this is a convenient little shortcut. The derivative of a reciprocal is the negative of the derivative over the square of the function. I didn't actually have to use the quotient rule. In other words, this is the result. I can skip all of this. That's kind of nice. Why am I showing you that? Because that's how we're going to do the next two. So here's what I want to do next. I want to find the derivative of the secant function. Well, isn't the secant function the same as 1 over the cosine? And I think this pretty much looks just like this. Yes, I can use quotient rule, but it's going to take extra time. Now, there's a really simple set of rules in life. I always refer to them as the rules of life, by the way. There's 3 major rules that all of you learned probably as children. Okay, first one, of course, is chew your food before swallowing it. Second one, of course, is keep all your limbs in the car while it's moving. The third one, of course, everyone knows is don't forget to breathe. Those I call the 3 rules of life. But a lot of people don't realize there's actually a 4th rule of life. Yeah, if all else fails, it doesn't matter where you are, what the situation is, if all else fails, change everything to sines and cosines. Some of you have learned this rule. Doesn't matter. You're stuck in the middle of the desert. You're dying of thirst. Just change everything to sines and cosines. A well will probably show up. I need to do a derivative of secant. Change it to sines and cosines. We needed to do the derivative of tangent. We changed it to sines and cosines. You see, because sines and cosines mathematically usually are very easy to work with. And now that we know how to do their derivatives, because we already knew their limits, they become actually more friendly. So in this case here, by changing this to 1 over cosine, I give myself a chance. There's no way I can use the definition of the derivative on the secant. I don't even know an expansion for the secant of alpha plus beta, but I do know what to do here. According to what I just said, my numerator should be, okay, the negative of the derivative of the cosine. That's the formula I just laid out for you. The derivative of the cosine is negative sine. So my numerator should be that over the square of my denominator. Now, if I had used quotient rule, I would have got this. It just would have taken a lot longer. So that answer is pretty simple. That answer is clearly just sine x over the square of the cosine function. Now, that is correct, but it's not the most useful form. It's actually far from the most useful form. First of all, it's a quotient of trig functions. There's never going to be a time when you give an answer that puts a trig function by itself in the denominator. So if my denominator was, 3 plus cosine, there's not much I can do with that. But if my denominator is cosine, then I don't have a denominator. I just have a secant somewhere else. So I can certainly bring this up as a secant squared. But here's the thing. I would then have a product of sine times cosine times cosine. That's 3 things. I'd like to write this as only 2 things. So we're going to be a little bit clever. How about if I think of this as 1 over cosine times sine over cosine? If I look at this in this form, then I will see the answer is simply secant x tan x, which is a smaller version of an answer than sine times secant squared, because sine times secant is tangent. So this is the universally accepted derivative of the secant function. Now let's similarly, in a different color, of course, let's do the derivative of the cosecant function. Okay, well, using this model here, that's the derivative of 1 over the sine function. And using the model that we just established, let's see. Well, I know my denominator is going to be sine squared. My numerator is going to be negative the derivative of sine. That would be cosine. Okay. So like this one here, if I pull it apart, now how should I pull it apart? Really in the same way. How about if I pull it apart as negative 1 over sine times cosine over sine? I know these are equal, and this gives me negative cosecant x cotan x. And now we have finished all of the trig derivatives. There are no more trig derivatives to take. We've just figured out how to differentiate all 6 trig functions. And we only needed the limit for sine and cosine. The rest of them, we simply used quotient rule, which is kind of nice. So I'm going to give you a quick summary here, and I'm going to show you something that not in the textbooks, but might make it easier for you to remember. Okay, so let's write them down. Okay, I'll write it like this. This is my f of x, and this will be f prime of x. So f of x Actually, I'm sorry, let me start with sine. I'm gonna go. Let's do it this way. My f of x is sine, cos, tan, cotan, secant, cosecant. What I'm doing is I'm pairing each of the trig functions with its what's called its cofunction. Just to show you that there's actually a pattern here that will help you remember. So the derivative here is cosine. Here it's negative sine. Here it's secant squared. Here it's negative cosecant squared. Here it's secant tan. Here it's negative cosecant cotan. So there's a couple of observations I want you to notice. First of all, the three cofunctions, their derivatives are negative. That's very important. The derivative of a cofunction is always negative. The other functions, sine, tan, secant, their derivatives are not negative, okay? That's actually huge. That the most common error by a mile is the plus and minuses. Putting a negative when it shouldn't, or not putting when it should. Now, how else are you going to remember? Well, if you can remember the derivative of sine, tan, and secant, then actually the other three are automatic. You see, let's start down here. The derivative of secant is secant tangent. What are the two cofunctions of secant and tangent? Cosecant and cotangent. So the derivative of secant is secant tangent. The derivative of its cofunction are the cofunctions here and a negative. Now let's go up to here. The derivative of tangent is secant squared. I got to remember that one. Now look at its cofunction. What's the cofunction of secant? Cosecant. So the derivative of cotangent is the negative of the co-derivative, if you will. Now the derivative of sine is cosine. The derivative of cosine is the negative of the, well, what would the co-derivative, well, what would the cofunction of cosine be? Back to sine. So it's an interesting observation. It's neither here nor there. But if you remember sine, tangent, and secant, then the cofunctions are negative and they're the co-derivatives. Just change all the things to co-things. And that, by the way, will always work. Now, as you practice, you will remember these because they're really important. The cosecant and the cotangent, like I said, are the most obscure. They come up the least, but they still come up. So now let's do more functions now that we have them. Let's do more examples. So now let's say I want to take the derivative, how about, of x to the third power over the cosine of x. I want to do this derivative. All right. Well, let's see. This will be the bottom times the derivative of the top minus the top times the derivative of the bottom over the square of the bottom. Okay. Now, everything I said is true and correct. Can I do better than this? Well, I can certainly factor out an x squared from the top. So let's do that. And then I would have 3 cos x plus x sine x all over the square of the cosine function. But I have a trig function in my denominator. Shouldn't that be on top? But if I try to multiply everything by secant squared, that might make it trickier. Instead, what if I put those together in that way? Oh, I can do that. I can break that up. So now I'd have x squared times what? Times 3 cos x over cos squared x plus x sine x over cos squared x. This is absolutely correct. And now I can simplify these guys. Aha. So cos x over cos squared would just be 3 over cosine. Sine over cos squared would be 1 over cosine times sine over cosine. So now we are where? X squared times 3 secant x plus x secant x tan x. Oh my goodness. And now if I factor out the secant, I'm going to have x squared secant x times, what am I left with? It looks like, did I already lose something here? I think we're left in with what, 3 plus x tan? Wow, that was a lot of work. Does anybody know a faster way I could have done this? Would there have been an easier, faster way to do this? Would there have been a way that I could have got this answer like in 1 or 2 steps? Well, what did we do here? We said we have a trig function in the denominator. That's not good. Look at the original problem. I have a trig function in the denominator. That's not good. So here's an absolute rule. If you can make a problem simpler before you start, always do that. You see, my final answer cannot be a quotient because my final answer cannot have a trig function in the denominator because its reciprocal would make it no longer a quotient. So here's what I should have done in step 1. How about if I had just written it like this in step 1? Oh my goodness, and then just use product rule? Yeah, if I had done this in step 1, then I would have first times the derivative of the second. Sorry, let me erase a little bit of this. Plus the second times the derivative of the first. And then when I factor out the GCF, boom, done. Because my GCF would be x squared secant. So in other words, 1 step derivative, 1 step factor, I'm done. And by the way, that's the most any problem should ever take you. So if I'm not paying attention, I used the quotient rule when I didn't have to actually do this as a quotient. Now, again, there are times when you don't have a choice. If you can't manipulate your quotient and make it simpler, then you take the derivative of the quotient. But if you can rewrite it as a product conveniently, then you always rewrite it as a product. Okay, the reason being product rule is simply easier to take than quotient rule, always. Let's do another one. And again, I've got notes and I got videos. I want to do the derivative of how about, let's do something ugly like cotan x over x to the 4th power. Well, obviously, my trig function is in the numerator, so doing quotient rule would be absolutely correct. But can I write this as a product? Yeah. And there's a couple of simple rules of thumb that I want you to notice. When your denominator is a trig function, obviously bring it to the top. If your denominator is something raised to a power, like x to a power, or even a quantity raised to a power, then bringing that up to the top as a negative exponent also turns out to be a way that perhaps will make your life easier. So in this case here, what I would like to do is I'm going to rewrite this as x to the negative 4th times the cotan x, because I know that's the same thing. Now, a negative exponent should not show up in a final answer because we would consider it not to be simplified. But you'll find that if you do it in this form, you'll get to your final answer sooner, and there will be just less manipulation. So when I do this, okay, first times the derivative of the second. Now, we showed that the derivative of the cotangent is the negative of the cosecant squared, plus the second times the derivative of the first. Bring the exponent down. Okay, I'm completely finished with the calculus at this point. So all that I have to do now is write this in its most useful form. There are 2 absolutely correct acceptable answers here. The first one is if I factor out the x to a power, that would be 1. The second would be just simply rewrite it as stated. So if I said factor out, I have x to the negative 4th, I have x to the negative 5th. Common factor would always be the smaller of the 2 exponents. Negative 5 is smaller than negative 4, and the exponents will always only differ by 1, by the way. So if I factor out x to the negative 5th, then I will have a whole factor of x left over because x times x to the negative 5th is x to the negative 4th. So I would have negative x cosecant squared. And again, quick check, x to the negative fifth times negative x is negative x to the negative fourth. Beautiful. Here, I factored out the entire x, so I'm only left with the negative 4 times cotan. Now put this guy downstairs. So I'm not worried about the fact that I have negatives. Yeah, you could factor a negative 1 out. I don't know if that makes things easier or more complicated. Perfectly acceptable answer. The alternate version of this, which is equally acceptable, is just go back to here and go back to here. Just put that downstairs. So that's now negative cosecant squared x over x to the fourth. And this is negative 4 cotan x over x to the fifth. Same answer. Now, if I had broken this up into two quotients, that's what I would have gotten. This answer or this answer are the best answers. And because trying to set either one of them equal to 0 would be really, really difficult because of the trig and the x's and mixing. I wouldn't even want to go there. So that's about as ugly as it's ever going to get. Okay. That's not hard. It's just a little bit more bookkeeping. So what should you be able to do after today? Certainly take the derivative of any of the 6 trig functions, because those are formulas. Now be able to take the derivative of any product of polynomials and trig functions, or take the derivative of any quotient of polynomials and or trig functions. Okay, well, there's a whole lot more functions. We've only gotten about 1/3 of the functions we're going to deal with. We still have exponential, logarithmic, inverse trig, hyperbolic. There's a lot more functions that we're going to have, but the development will look a lot like this. So again, refer to the notes and the extra stuff that I've posted now for practice. This is very mechanical. You're not using definition of the derivative when I ask you to take the derivative. You're just using now the formulas we've derived. So practice is critical, and hopefully you get really good at this really, really fast. Okay. Let me pause the recording.